Hi guys, let's talk about the next part of thermochemistry, and that is representing enthalpy. Enthalpy changes can be represented in four different ways. One is when you can write down thermochemical reactions with energy terms. Next is when we represent thermochemical equations or reactions with delta H values. Next way of representing enthalpy changes is with the help of molar enthalpies of reactions. And the last one is potential energy diagrams. Let's talk about the first type first. This is type 1, and let's take a chemical reaction where water is breaking down to give you hydrogen and oxygen. As you can see, this is a balanced chemical reaction between water, hydrogen and oxygen, where water is your reactant and hydrogen and oxygen are your products. This reaction involves water to gain energy in order to break it into its components. Now that energy gain can be represented as numbers. So now this reaction is a complete reaction where water gains 285.8 kilojoules of energy in order to form hydrogen and oxygen. We can clearly see as the water has gained energy, or whenever you see energy on the reactant side, or whenever you see the numbers added on the reactant side, this will be a representation for an endothermic reaction. Why is this called an endothermic reaction? Is because the reactants have gained energy in order to form the products. Let's take another example for this type. In this reaction, magnesium reacts with oxygen. We will straight away write down a balanced chemical reaction because I'm not testing your balancing skills here. This results in the formation of magnesium oxide. And this reaction is an exothermic reaction where the reactants are going to release energy in order to form products. So the energy is going to be then written on the right side. So this is a type of an exothermic reaction. How can we read this reaction? Is when magnesium reacts with oxygen, it gives us magnesium oxide and 601.6 kilojoules of. Let's talk about the second type of representation now. The second type of representation, I'm going to take the first and the second equations of first type in order to compare the first type with the second type. So if we have the same reactions, we have water that gives us hydrogen and oxygen, and this is a balanced chemical reaction. Now the second type says that we have to write down thermochemical equations that we have already written with delta H values. So all we have to do is on a little bit distant away from the equation, you just have to mention delta H, because delta H is the energy gain or loss or enthalpy change, as we have already discussed in the previous videos. We just write it down as delta H is equal to positive 285.8 kilojoules. So this reaction and the first reaction here, it just mean the same thing. The only difference is that it's a different way of representing, and this is a different way of representing. Here we write down energy on the side as delta H. Because the reaction is an endothermic reaction, we just mentioned this plus sign here. The next example, let's talk about magnesium reacting with oxygen, giving us magnesium oxide. As we know that this reaction is an exothermic reaction because energy is released on the product side, we just write it as delta H. In this case, we would put a negative sign because it's an exothermic reaction, and all we have to do is just write down this number. So this is the second type of representation. We'll talk about the third type, and the third type is representing the enthalpy changes using molar enthalpies. So if we have to use molar enthalpies, all we have to do is just write down delta H. We do not have to write down the equation in this case. We just write on delta H, and then this not sign. This represents molar enthalpy. Just delta H is change in enthalpy. Delta H not sign means change in molar enthalpy, change in enthalpy for 1 mole of reactant. Now for writing standard molar enthalpy, all we have to remember is that we need to know what type of reaction is taking place. For example, if sodium reacts with bromine to give you sodium bromide, and when we balance the reaction, this reaction looks like this. Here, sodium bromide is being formed. So this is a formation reaction. Now we need to make sure that the formation of the substance that is being formed in the reaction should be only for 1 mole. This is a 2 mole reaction. So for example, let's say delta H for this reaction is 722.82 kilojoules. This is not for 1 mole. Delta H naught means for 1 mole. So since this is not for 1 mole, I'm just going to write it as delta H. But if I want to represent it as a molar enthalpy, all I have to do is I just have to divide this by 2, because I have a total of 2 moles for sodium bromide being formed in this case. I would have to do 722.82 divided by 2, and that would give me 361 kilojoules per mole. Now, does this show us if this reaction is endothermic or exothermic? I have to represent either a plus or a minus sign. Formation reactions are mostly exothermic, so this reaction is an exothermic reaction. So our final answer for representing delta H naught in this case will be delta H naught F equal to negative 361.41 kilojoules per mole. So in order to know the reaction, and since here formation is happening, we just write on delta H naught F. Let's take up another example, and in that example, let's say combustion of methanol is taking place. What is methanol? As we have done organic chemistry already, so methanol is CH3OH. Combustion reaction means it burns in the presence of oxygen in order to give you carbon dioxide and water. This is a type of complete combustion. If I want to represent it as a molar enthalpy, all I would have to do is, because it's a combustion reaction, so I will write down this subscript as C, and this is molar enthalpy, so I will put this not there. This reaction gives out 726 kilojoules of energy. So in this case, I'm going to write down this much per mole. This per mole means it's a molar enthalpy. Talk about enthalpy diagrams. This is the fourth way of representing your enthalpy changes. Enthalpy diagram looks like this. You just have to make axes. On your y-axis, you have to put an EP, that's the potential energy. Make sure your axes are labeled. And on your x-axis, you have to write on reaction progress. As your reaction progresses, what is going to happen is you're going to change from you're going from reactants to products like this. So your reactants have high energy, your products have low energy. If this is the scenario, this means it's an exothermic reaction. And if we need to represent endothermic reaction, this is how our EP is going to be represented. This is the reaction progress. In case we are making an endothermic reaction, this is how we would make reactants. And this is how we would make products. If your products have a higher energy than reactants, then it's called an endothermic reaction. See here, let's take the same two reactions that we discussed in type 1 and type 2. The first reaction that we discussed was water takes 285.8 kilojoules of energy in order to give hydrogen and oxygen, and this is an endothermic reaction. So we would represent that reaction on endothermic reaction diagram. This is your endothermic reaction diagram. The reaction that we are representing on this diagram is an endothermic reaction where water gives us hydrogen and oxygen and releases energy equal to 285.8 kilojoules. So all we have to do is we have to make reactants below the products. So this is my reactants, and on the reactants I just write on water because that's my reactant. On products I just write on my products, and that is hydrogen and oxygen. Because I'm going from reactants to products, I'm going to make my arrow like this, and here I will be writing down delta H is equal to 285.8 kilojoules, and this is my final potential energy diagram for this particular reaction. This was our second reaction. So we will deal with this reaction now. Magnesium reacts with oxygen in order to give magnesium oxide and 601.6 kilojoules of energy, and this is an exothermic reaction. So we would represent it on an exothermic general potential energy diagram. In this case, we would make reactants on top of products, and reactants are magnesium and oxygen react to give you magnesium oxide because energy has decreased as the reactants have lost heat. And how much amount of heat the reactants have lost is 601.6 kilojoules. This negative sign represents that the reactants have lost heat, and this is an exothermic type of diagram. With this, we are done potential energy diagrams.